In 1978, a recalculation of the 59-story Citicorp Center exposed a mathematical reality its builders did not want to believe. At the time, this finished tower, standing over Midtown Manhattan, was celebrated as a masterpiece of modern engineering. Its original blueprints were rigorous. It fully complied with every building code of the era. Yet just 1 year after its doors opened, a revised calculation proved it was heavily compromised. This chart plots the frequency of severe weather events in New York. The red line intersecting the failure threshold indicates the precise wind speed required to trigger structural collapse. That threshold sits precisely at the 16-year mark. A 16-year storm is not an anomaly. It is a standard meteorological event that anyone sitting at a desk on the 40th floor could reasonably expect to live through. The flaw that brought the tower to the edge of failure did not stem from gross negligence. It was the result of an inventive synergy between an inventive architectural design, standard construction substitutions, and physical vectors the rulebook never demanded engineers check. Strict regulatory compliance, it turns out, is no guarantee of survival against physical reality. The physical anomaly began on the ground. When Citicorp acquired the block, they negotiated with St. Peter's Lutheran Church, occupying one corner of the lot. A standard high-rise relies on a simple vertical frame, transferring mass straight down through 4 main columns, placed at the extreme corners of the footprint. But the church demanded a new sanctuary on the exact same spot. A corner column would have driven straight through their roof, forcing engineer William LeMessager to eliminate the corners entirely. To clear the airspace over the church, LeMessager shifted the 4 massive support columns away from the corners, placing them precisely at the midpoints of the building's 4 faces. This shift severed the traditional path gravity takes to pull weight down to the bedrock. The 59-story structure was hoisted onto 4 9-story stilts, creating massive structural voids at the corners where support would normally sit. Accommodating a single localized real estate constraint forced a systemic redesign of how the entire tower absorbed and directed basic physical forces. To stabilize a tower resting on midpoint stilts, LeMessager designed a system of stacked diagonal braces. These V-shaped chevron braces acted as a funnel, gathering the vertical mass of the upper floors and the lateral shear of the wind, driving those forces straight down into the midpoint columns. The New York City Building Code of the 1970s only required engineers to calculate stability based on orthogonal winds. Orthogonal winds strike a single flat face of a building head-on at a 90-degree angle. On this model's left side, wind hitting a flat face spreads force evenly across a wide network of chevron braces, keeping stress within code requirements. But an inquiry from an engineering student named Diane Hartley prompted LeMessager to investigate a vector the code ignored: quartering winds. A quartering wind strikes the corner directly, hitting 2 adjacent faces at a 45-degree angle. On the diagram's right side, this strike aligns perfectly with the diagonal axis. Pressure violently concentrates along a continuous diagonal path, stripping the tower of structural redundancy. When LeMessager ran the math on this localized pressure, the results showed that quartering winds increase the force load on specific chevron braces by 40% over the orthogonal standard. A rigid frame designed to dissipate direct flat pressure becomes dangerously fragile when force isolates down a single seam. During construction, the steel fabricator proposed a modification to optimize the budget, swapping the original full penetration welds for bolted joints on the diagonal braces. A proper weld fuses 2 pieces of steel into one continuous member. A bolted joint requires severing the steel and connecting the 2 halves with a flat plate and a mechanical grid of bolts. Bolted joints possess inherently less tensile strength and a lower capacity to absorb localized stress than a fused weld. That 40% load increase traveled down the chevron braces and slammed into the weakened bolted connections. The bolts provided less resistance, so the stress concentration didn't rise by 40%. It damplified to 160%, instantly exceeding the steel's yield limit. The building's survival rested entirely on a single active defense system, a tuned mass damper, consisting of a 400-ton concrete block floating on pressurized oil. As the wind pushes the building, the damper dynamically slides in the opposite direction, physically canceling out the sway and relieving the immense pressure on the bolted joints. But the pressurized oil bearings keeping that 400-ton block afloat require constant electrical grid power to function. The massive storms capable of generating fatal quartering winds are the exact weather events most likely to cause local blackouts, completely neutralizing the damper. Relying on a dead damper, mathematical reality dictated that the bolted joints would shear in a standard 16-year weather event. Swapping welds for bolts was a rational economic decision in isolation. Stacked against untested wind vectors and a grid-dependent damper, it engineered an invisible multiplier for catastrophe. Faced with his own fatal data, Le Messager went to the building's owners and insurers. They initiated immediate structural reinforcement without ordering an evacuation or alerting the public. Leaking a high probability of collapse for a major skyscraper into the dense pedestrian environment of Midtown Manhattan risked triggering mass panic. The remediation was executed entirely in the dark. Specialized construction crews operated strictly from 11 at night until 6 in the morning. Night after night, crews cutting through interior walls used torches to weld heavy 2-inch thick steel plates directly across more than 200 vulnerable bolted joints. By dawn, the drywall was replaced, leaving the daily workforce entirely unaware of the compromised skeleton surrounding them. In early September of 1978, midway through the welding operation, an unscripted variable emerged in the Atlantic, Hurricane Ella. This meteorological map shows Ella tracking directly toward the eastern seaboard, pointing straight at New York, while the skyscraper's joints were only partially reinforced. As emergency officials quietly prepared for an evacuation, Ella diverted out to sea at the last moment, sparing the city and allowing the welders to finish without the partial system ever taking a real-world load. Despite the rigorous retroactive engineering, the survival of the structure in that critical window ultimately relied on blind meteorological luck. Once the steel plating was complete, the fully welded tower possessed a revised survivability threshold, capable of withstanding a 700-year storm event. The financial settlements were handled quietly, and the near miss was kept completely secret from the public for 17 years. The failure of the original blueprints was not born from carelessness. It was the product of strict adherence to an incomplete regulatory code. The actual safety of a complex system does not live in its theoretical design. It lives in the continual reassessment of its minor components against real-world physics. The building stands today because an engineer chose to actively recalculate his own accepted work based on a student's inquiry, choosing empirical data over his professional reputation. True structural integrity requires viewing every routine decision and every standard assumption as a potential failure point waiting for the precise angle of attack.